Hello, I am Olubenga Oshakwadi, a presenter at the Virtual Conference on Chemistry and its Applications 2020. My seminar is titled Bulk and Surface Properties of Liquid Bismuth Tin Alloys Using an Improved Quasi-Lattice Theory. The seminar is born out of a research work carried out by O.E. Awe and myself. We are both domiciled at the University of Ibadan. Our interest in bismuth tin is because it is a lead-free solder candidate. The knowledge of the bulk and surface properties of bismuth tin will help in determining its suitability in certain applications. A lot of experimentalists have worked on bismuth tin, and some results have been summarized in the repository by Altgreen et al. 1973. The result for bismuth tin in this repository is given at 600 Kelvin. We are aware that bismuth antimony tin, a supersystem of bismuth tin, has been studied both experimentally and theoretically at 900 Kelvin. The knowledge of the thermodynamics of bismuth antimony, bismuth tin, and antimony tin at 900 Kelvin will provide better understanding of the thermodynamics of bismuth antimony tin, and this has motivated this study to be carried out both at 600 Kelvin and 900 Kelvin. Because of limited time, permit me to talk briefly on the quasi-lattice theory. The quasi-lattice theory for compound forming liquid alloys, which I will be calling QLT, was developed by Bhatia and Sen in 1984, and it is popular for its consideration of coordination number. It reduces to the conformal solution and Floris approximation of Bhatia and Agrove 1974 when coordination number is 2 or infinity. The QLT has the ability to describe alloy systems in terms of the relative bonding energies between atom pairs, and it is known to be successful in the study of concentration fluctuations in the long wavelength limit. The QLT by Bhatia and Sen 1984 has been extended by Awa et al. 2006 to study ternary systems, and the extended model requires the knowledge of the binary subsystems of the ternary of interest. The use of QLT in previous studies on physical systems has been applied with coordination number set as 10. The use of 10 as coordination number in all systems at all temperatures and alloy compositions may be a good approximation. However, improvements can be made by applying more recent knowledge, such as the knowledge of crystalline materials, which tells us that coordination number depends on the nature of materials, and coordination number depends on temperature. This has been reviewed by experimental results. Even theoreticians have also modeled coordination number with respect to pair distribution functions, and pair distribution functions are temperature dependent. It also makes sense to say coordination number will depend on alloy composition, that is the proportion of components in the alloy systems. The improved QLT used in this work applies coordination number that depends on nature, temperature, and composition of the system. Theoretical formalism. We have adopted the model developed by Tao 2005, which is equation 1, to estimate coordination numbers of pure liquid metals at required temperatures, and that is represented by Z subscript I. Equation 2 was introduced to approximate the average coordination number based on the alloy composition. It depends on the coordination numbers of the pure components and their molar fractions. See subscript I. The average coordination number is represented by z caret. That is equation 2. The z caret here talks about average coordination number. From this point, it is more convenient to discuss in terms of average coordination numbers instead of the nominal coordination numbers used in crystalline materials. Equation 2 here is expanded by applying equation 1 to obtain equation 3, and other variables are defined below here. Table 1 shows the coordination number of pure bismuth and pure tin estimated at 600 and 900 Kelvin by applying equation 1, the model of Tau 2005. The relevant parameters used in the estimation are also included. Equation asterisk here is used in estimating average error. The average error estimation is used to quantify the agreement between two sets of data, especially existing and predicted data. Now, the quasi-lattice theory. The quasi-lattice theory of compound forming alloys by Bhatia and Sen 1984 assumes that Na moles of element A and Nb moles of element B will mix to form a pseudo-ternary mixture that will result in N1 moles of unassociated atoms of element A, N2 moles of unassociated atoms of element B, and N3 moles of A-mo-B-no complex, where the total number of moles in the mixture is N. Then mathematically, Na plus Nb equal to N. That is the law of conservation of matter. C1 is the molar concentration of element A, while C2, which is as good as 1 minus C1, is the molar concentration of element B. Equations 7 and 8 were obtained from the law of conservation of matter, while equations 9 and 10 give expressions for Gibbs free energy of mixing, which is shortened as GM. I'll be calling Gibbs free energy of mixing GM. In order to be brief, I would like to call your attention to equation 14. The z caret in equations 14 to 16 implies the use of average coordination number instead of the nominal 10 used in previous work on QLT. Without boring you with in-depth definition and derivations, let me go straight to the application. GM, equation 14, is applied by fitting four interaction parameters, that is G, mu12, mu13, and mu23. These parameters are fitted while we compare the resulting GM with existing GM, mostly experimentally obtained GM, at all compositions. The fitted parameters, while predicting GM, must agree with the equilibrium conditions given in equation 17. Equation 17 is a partial differential of GM with respect to N3 and is given in equation 18. Expression Q in equation 19 helps in simplifying equation 18. So in our fitting, we ensure that equation 18 is satisfied while conforming equation 14 to available experimental data. Equation 20 relates thermodynamic activities to Gibbs free energy of mixing. And when solved for components A and B, equations 21 and 22 were obtained. It is important to note that composition-dependent average coordination number was put into consideration while differentiating GM in equation 20. Table 2 presents the interaction parameters used in fitting the Gibbs free energies of mixing in bismuth tin at 600 Kelvin and 900 Kelvin. This set of interaction parameters fulfilled the equilibrium condition and also agreed with experimental data. The agreement with experimental data was measured by average error estimation, that is equation asterisk, and the results are also displayed here. Figure 1 shows plots of experimental and predicted GM against molar fraction of bismuth at 600 Kelvin and 900 Kelvin, while figure 2 shows plots of experimental and theoretical thermodynamic activities of bismuth and tin at 600 Kelvin and 900 Kelvin. The agreement between predicted and experimental data for GM and thermodynamic activities is very satisfactory at both temperatures. Enthalpies and entropies of mixing can be obtained from Gibbs free energies of mixing using the thermodynamic relation presented in equation 23 and equation 25. Equation 24 is obtained by solving equation 23, while equation 26 is obtained by solving equation 25. Integral enthalpies and entropies of mixing requires the fitting of partial differentials of interaction parameters with respect to temperature while applying the previously fitted interaction parameters. So this is the differential of the interaction parameters, and while the interaction parameters are also in the are also available in this equation. The differentials of GM with respect to temperature were carried out with the consideration of temperature-dependent average coordination number. The differential of average coordination number with respect to temperature is given in equation 27. Equation 27 is based on the model used in computing the coordination number of pure liquid components, which in this case is the model by Tao 2005. If you decide to carry out a similar research using another model to compute coordination numbers, then you will need to define your own equation 27. Concentration fluctuations in the long wavelength limit, that is SEC 0, and Warren-Cowley short range order parameter, that is alpha 1, were computed for bismuth tin at 600 Kelvin and 900 Kelvin. SEC 0 gives information about the nature of atomic order, that is, it predicts the type of nearest neighbor that will associate with a central atom. It determines whether like atoms or unlike atoms will be preferred as nearest neighbors. SEC0 is not useful alone. Its ideal values at, at the particular composition is also required to make inferences. SEC0 is defined in equation 29, while its ideal is defined in equation 30. Alpha 1, defined in equation 31, also give information about the nature of atomic order, and it also includes the extent of the order. Alpha 1 ranges from -1 to +1. When alpha 1 is -1, it means complete order, while +1 means complete segregation, while 0 means random distribution of atoms. When SEC0 is greater than its ideal, or alpha 1 is greater than 1, it implies preference for like atoms, that is, tendency for homocoordination or segregation in the mixture. And when SEC0 is less than its ideal, or alpha 1 less than 1, it implies preference for unlike atoms, that is, tendency for heterocoordination or atomic order. So let's move to surface concentration and surface tension. Equation 32 was used to determine the surface tension and surface concentration of bismuth tin at 600 and 900 Kelvin. Sigma is the surface tension. Sigma is the surface tension of the bismuth tin mixture, while sigma 1 and sigma 2, this is sigma 1 and sigma 2, are the surface tensions of pure bismuth and pure tin respectively. The surface tension for pure bismuth and pure tin is given at 600 and 900 Kelvin in table 3. That's this table. In equation 32, C1 is concentration of component 1 in the mixture, while C1s is the concentration of component 1 at the surface. Component 1 in this case is bismuth. And gamma 1 is the activity of component 1 in the mixture, while gamma 1s is the activity coefficient. Gamma 1 is the activity coefficient of component 1 in the mixture, while gamma 1s is the activity coefficient of component 1 at the surface. And component 1 here is still bismuth, while component 2 is tin. The surface concentration and surface tension of the mixtures were simultaneously obtained from equation 32 by solving it numerically. Results and discussion. The integral enthalpies and entropies of mixing were studied at 600 Kelvin. Table 4 shows the partial differentials of the interaction parameters fitted to conform to experimental data. It also shows the average errors in computed enthalpies and entropies. The plots of normalized integral energies of mixing and integral excess entropies of mixing are shown in figure 3. In figure 3, the solid line represents the QLT computed HM over RT, while the triangles represent the experimentally obtained values. The dashed line represents the QLT computed excess Sm over Rt. Sm over Rt is excess integral entropies of mixing. And the squares represent the experimentally obtained Sm over R. The experimental values were retrieved from the repository by Altgren et al. 1973, and they agree with the QLT computations satisfactorily. The enthalpies exhibit positive deviation from Raoultian behavior in all composition range and appears to be symmetric about the equiatomic composition, while the excess entropies are negative and asymmetric about the equiatomic composition range. Figure 4 shows the SEC0 for bismuth tin at 600 Kelvin and 900 Kelvin. It also shows the ideal SEC0, which is represented by the dashed lines. The plots in figure 4 show that SEC0 is greater than SEC ideal. The SEC0 is greater than SEC ideal. At both temperatures and in the entire composition range. This implies preference for like atoms as nearest neighbors in the mixture. Also, alpha 1 for bismuth tin at 600 Kelvin and 900 Kelvin, which is plotted in figure 5, is greater than 1 in the entire composition range. This agrees with the information obtained from SEC0 through figure 4. The alpha 1 peaks at about 40% bismuth composition with a value of about plus 0.015. During theoretical formalism, I mentioned that alpha 1 ranges from -1 to +1. Therefore, the peak of about plus 0.015 infers slight homocoordination property exists in the bismuth and tin systems. In other words, there is a slight tendency or slight preference for like atoms as nearest neighbors. It can also be observed that at about 35% bismuth and above, segregation tendency increases with rise in temperature, while the reverse is the case at about compositions less than 35% bismuth. Figure 6 is a graph of surface composition of bismuth against bulk concentration of bismuth at 600 Kelvin and 900 Kelvin. It can be observed that as the bulk concentration of bismuth increases, the surface concentration also increases. And it can be observed that at about 10% bulk concentration of bismuth, about 40% bismuth is observed at the bismuth tin surface at 900 Kelvin. And about 60% bismuth is observed in the bismuth tin surface at 600 Kelvin. The surface concentration of bismuth is greater than its bulk concentration in all compositions, and at both temperatures. Therefore, it can be deduced that the surface of bismuth tin is enriched with bismuth within the temperature range of 600 Kelvin and 900 Kelvin. The surface concentration of bismuth decreases as temperature of bismuth tin rises. This can be implied by the graph for 600 Kelvin, the solid line, which is greater which uh, which shows greater surface concentration values for bismuth in the entire composition range. Since the surface concentration of bismuth and tin add up to 1, it can be deduced that the surface concentration of tin increases as temperature of bismuth tin rises. I will expect a plot of surface concentration of tin, that is CSNS, against the bulk concentration of tin, CBI, to be of this form. That means this graph of surface concentration of bismuth against the bulk concentration of bismuth is sufficient to describe what happens with tin, because the surface concentrations add up to 1 while the bulk concentrations of the components add up to 1. Recall that surface tension and surface concentrations for certain compositions and temperatures were obtained simultaneously. Figure 7 shows the surface tension for bismuth tin at 600 Kelvin and 900 Kelvin. The most glaring deduction is that surface tension reduces as temperature rises, and this agrees with basic concept of surface tension. These plots have concave shape. They have concave-like shape, which agrees with many studies on surface properties that the component with lower surface tension, in this case bismuth, has the greatest surface enrichment. This can be confirmed in figure 6 here, and table 3 that shows the surface tension of pure bismuth and pure tin. Conclusion: this work started by fitting the Gibbs free energies of mixing by using interaction parameters that fulfilled the equilibrium conditions and conformed to experimental data. These fitted parameters were observed to reliably predict the thermodynamic activities of bismuth and tin at both temperatures, that is 600 Kelvin and 900 Kelvin. The same set of interaction parameters were used while fitting their temperature derivatives to model the integral enthalpies and entropies of mixing. Thereafter, SCC0, alpha 1, surface concentrations and surface tensions were computed for bismuth tin at 600 Kelvin and 900 Kelvin. It is worthy of note that nature-dependent, temperature-dependent, and composition-dependent coordination numbers were incorporated in the QLT developed by Bhatia and Sen 1984. The integral enthalpies of mixing exhibited positive deviation from Raoultian behavior and is symmetric about the equiatomic composition. The integral excess entropies of mixing is negative in all composition range and asymmetric about the equial atomic composition. XCC0 and alpha 1 revealed slight segregation tendencies in bismuth tin. Surface property studies reveal that bismuth atoms segregate to the bismuth tin surface, which is confirmed for temperature range of 600 Kelvin to 900 Kelvin. And the enrichment of bismuth atoms at the surface reduces with temperature, while the enrichment of tin atoms at the surface increases with temperature. The concave nature of the surface tension graph agrees with popular knowledge that bismuth, which has the lower surface tension, has the greater surface enrichment. Finally, the application of the newly improved quasi-lattice theory was successful. These are the references used in the slides and the presentation. Acknowledgement. I am grateful to Mrs. Fumilola Taiwo for funding my conference attendance. Thank you for listening.